It is a great pleasure and honor to introduce today's speaker, Professor Nigel Bishop, who studied at the University of Cambridge. He was tutored by Stephen Hawking, who would become one of the most famous relativists of our time. He obtained a BA honors degree in mathematics and moved to the University of Southampton, obtaining a PhD degree in 1976. At the same time, he was elected as a fellow of the Royal Astronomical Society. He was appointed as a lecturer at the University of Witwatersrand, and his first appointment as full professor was at UNISA in 1992. In 2009, he moved to Rhodes University as professor and head of the Department of Mathematics. He retired in 2016 and is currently emeritus professor. He has held several visiting appointments in England, University of Cambridge, University of Southampton, Germany, Max Planck Institute for Gravitational Physics, India, Inter-University Center of Astronomy and Astrophysics, Turkey, Sabanci University, USA, University of Pittsburgh, Louisiana State University, California, Institute of Technology. He has served as president of the South African Gravity Society. For many years, he has been on the council of the South African Mathematical Society, serving 2 terms as president. Internationally, he served at the Council of the International Society on General Relativity and Gravitation. He is the author or co-author of over 70 scientific publications and 3 books. The subjects of this work range from mathematical analysis to computer programming, from quantum gravity to discoveries about the horizons of black holes, and from cosmology to the theory of travel faster than light. However, for about the last 30 years, the focus of his work has been on gravitational waves, and in particular, how they are calculated. Professor Bishop, we look forward to your talk.
Okay, thank you very much. All right, let me start the screen share and just hope that it works. Share. Okay. And we go to presentation. Okay, does everybody see the slideshow?
Yes, they're visible.
Okay, that's great. Okay, so let me start. So I'm talking about observations and the damping of gravitational waves by matter. And if you're interested in what I'm saying, I'll leave out a lot of details in this talk. It's all in these 3 papers listed here. And this was joint work with Monas Naidu, who completed his PhD on this work, and also with Piet van der Walt. Now, the history of what I'm talking about actually goes back a long time. I mean, the first paper was by that I'm aware of on the subject was by Stephen Hawking in 1966. It was part of his PhD, and these are some of the other relevant publications that I'm listing that describe the previous work. I'm not going to give a historical review, but what I want to do is just give an idea of the state of the subject really before we started doing this work. So the first comment is that a non-dissipative fluid does not absorb energy. I mean, there has to be some if gravitational waves are to transfer energy to matter, there has to be some mechanism for that to be done. So something like dust can't absorb energy. But if the fluid has shear viscosity, then the fluid will be sheared by gravitational waves passing through it, and energy will be transferred to the fluid. And I mean, this was realized long ago. All right, and the formula for the way in which the magnitude of the wave is changed is given here. That it will decay slightly by exponent of -8 pi eta delta, where eta is the viscosity and delta is the distance through the fluid that it propagates. All right, so that might seem like a significant effect, but when one starts putting in actual values, this formula is in geometric units where the speed of light is 1 and the gravitational constant is 1. If you translate to SI units, you've got to multiply by g over c cubed, and that's tiny, 10 to the minus 36. So to consider the, common fluids in SI units have viscosities of order 1, something like 10 to the minus 3 for water, 10 to the 1 for syrup. Typical astrophysical viscosity values can be very high under extreme conditions. So the highest value I've seen is 10 to the 25 at the core of a supernova. But this occurs in a region of, in a tiny region, a region of 10, maximum 100 kilometers, which is up to 10 to the 5 meters. So if you take, even taking 10 to the 25 times 10 to the 5, doesn't get you anywhere near 10 to the minus 36. And astronomical distances are large, 1 gigaparsec. We've seen gravitational waves from further away than that is about 10 to the 25 meters. But if there's to be a significant damping effect, you would require an unrealistic viscosity for the intervening matter. Thus, although it's known that matter can extract energy from gravitational waves, it's commonly regarded that this effect is absolutely tiny and is ignorable from an astrophysical point of view. And that's what we wanted to look at again. So there's certain questions which we asked. Could the phase of, could matter, although it may not extract energy from gravitational waves, it may affect the phase, and that may be measurable. And also, wavefronts are spherical, not planar. Could that be important? Okay, and we're going to start looking at those questions now. So the formalism that we're going to use is the so-called Bondi-Sachs formalism, where the coordinate system is based on outgoing null cones. So, a null cone is a cone on which light rays travel. So a light ray traveling radially outwards in this diagram, the time coordinate u doesn't change, it just moves in a way instantaneously from one value of r to another. All right, and then we use standard spherical polars within the null cone. So the mathematical formalism was introduced in 1962 and is the formalism that was used to show that gravitational waves do carry energy. And the Bondi-Sachs metric describes a general space-time, and it's written down here. I won't go into any of these details, but I think that the important things to just take away are the coordinate system that u is represents is a coordinate on a null cone. So something traveling at the speed of light has u equals constant. R is what's called a surface area coordinate, so that the area of a sphere is 4 pi r squared. All right, so that then constrains the angular part of the metric HAB, so that its determinant must be that of a unit sphere metric. Right, and then this is technical, but it's convenient to reduce the number of, one can reduce the number of terms by representing the angular part of the metric by a single complex number. All right, although HAB is a 2 by 2 matrix, 2 by 2 symmetric matrix, you'd think it would have 3 independent components, but because of the area condition, there's a constraint in it, there are only 2. So you can actually represent it by a single complex number. And if you're familiar with this, these are the technical technical details as to how it's done, but we won't need those technical details in this discussion. And then J non-zero characterizes a deviation from spherical symmetry. And in an appropriate gauge, J is equivalent to the standard polarization states of a gravitational wave. So J is H plus IH cross. All right, now a source emitting gravitational waves at constant frequency dominated by the quadrupolar part, and in practice that's what happens. The main part of a gravitational wave signal is the so-called quadrupolar part, which is at L equals 2. And we can model that by small perturbations about Minkowski space-time. And in Minkowski space-time, all we do is we go back here, we put everything 0. So that this term becomes UA is 1, WC is 0, e to the 2 beta is 1. So this just becomes minus du squared minus 2 du dr plus r squared d theta squared plus sine squared theta d phi squared. So that would give you Minkowski space-time. And then we look at small deviations from that. And we write down the metric quantities in this form here. I mean, what we're doing is a standard separation of variables approach. So what we've got is a solution that's sinusoidal in time, and the angular dependence is given by a spherical harmonic. If you're not familiar with, I mean, these are particular types of spherical harmonic, but again, the details aren't important for this presentation. You can just think of these quantities, these L as this SC, LM as being a spherical harmonic. All right, then we can write the Einstein equations as RAB minus 8 pi TAB minus half GAB T equals 0. And separation of variables has reduced all the equations to ordinary differential equations in R. I mean, technically it's more complicated, but it's exactly what one does in a first course on ordinary differential equations, the separation of variables technique. As long as you choose your eigenfunctions correctly, everything works. Right, then we let F represent beta U W C J. Let M be a linear differential operator representing the Einstein equations linearized about Minkowski, and with TAB equals 0, and we can write abstractly MF equals 0. And the solution was obtained in 2005 and takes this form here. And the convenient point about this solution, I mean, those of you who've looked at solutions in general relativity, they're usually quite long and complicated. This is remarkably simple, and it's so easy to work with from an analytic point of view. All right, we use FM to denote the above solution, and note FM0 to denote the solution with CN0 equals 0. This bit here represents a gravitational wave that's incoming, and these bits here represent a gravitational wave that behaves as e to the as sinusoidal times the frequency times u, and u is just t minus r. All right, whereas this would be this term when you translate it into r is gives you sine t plus r. So it's an incoming wave, and the other part is the outgoing wave. Right, and if we look at the gravitational wave strain, what we find is that it's determined entirely by this constant C40 and the frequency. So C40 is determined by the physics, and the other constants that appear in this solution are gauge freedoms. All right, so now let's go on to the physical problem we're going to try and solve to look at how we would try to model the problem of matter, gravitational waves interacting with matter. So what we consider here is a source All right, surrounded some distance away by a spherical shell of matter. All right, and the spherical shell has got thickness delta. All right, and then the idea will be later, if we want to represent a more complicated source, we can represent it as one spherical shell after another, and then perform an integration. Because everything's linear, that will work fine. So the shell has a spherically symmetric density profile that vanishes at its boundaries at R0 and at R0 plus delta. All right, it turned out that the calculations become algebraically complicated, and it turned out that we needed a specific form for the density profile in order to be able to handle them using computer algebra. But what we found is we took a density profile, say this example here, we obtained certain results. We then repeated the work with a number of other density profiles and found that, well, to leading order, the results depended only on the shell mass, not on the details of the matter distribution within the shell. So that one can then, it's then reasonable to say, though it's not formally proven, that the results that we're going to obtain depend only on the shell mass, and that the specific form of the density function doesn't matter. We've tested that for a few cases. Obviously, that's all one can do with on a computer. All right, so the only non-trivial Einstein equations in spherical symmetry are these two, and we can solve them easily inside the shell and outside the shell, and these are the solutions, where ms is the mass of the shell. The solution within the shell is straightforward to obtain, but is a long, complicated expression, as one might expect, as one has a somewhat non-trivial density source, and there's no point giving it. But it's there in the computer algebra output in the paper. All right, so now what we need to do is to look at the perturbed solution in three different regions: the interior, within the shell, and in the exterior. Right. Within the shell, we know that the background geometry is Minkowski. That goes back to a theorem of Newton that says that there's no gravitational field inside a spherically symmetric shell. All right, but it's not explicitly so, since these quantities, beta b and wb, are not zero. All right, but that can be resolved by making a transformation to local Minkowskian coordinates by means of this expression here. So in these coordinates, the solution Fm applies, although the boundary conditions may introduce small corrections to the integration constants. Thus, we use Fm with this solution and then transform it to the global coordinate system. And we have a solution which we denote as Fi. Within the shell, the calculations are technically quite complicated. All right, but what we do is we evaluate the conditions that the conservation of energy condition with the metric terms evaluated using Fm0, right? Because we're working to linear order, that's fine. Then TAB, the right-hand side, is expressed as explicit functions of R depending on these various parameters. Einstein equations are linearized about a non-Minkowskian background, introducing terms of the form beta b or WCB times a metric perturbation. We use Fm0 to evaluate the metric perturbation, and these terms then become explicit functions of R depending on known parameters. Then our problem reduces to this: MF equals minus rho C times some known function. Right, so this and this MF is a linear differential equation operator. So then standard theory for linear differential equations says that the solution to this system is the solution to the homogeneous part, where we say MF equals 0. And that we already know. I mean, that was the solution we worked out a few slides back. We worked that out and we got this solution here. All right, and then plus a particular integral when we take account of the right-hand side, which is now an explicitly known function. All right, now actually finding that particular integral is non-trivial, but I won't go into that. And we denote the solution within the shell as Fs and introduce more additional constants. And similarly in the exterior, well, there we just have to deal with metric perturbations times the background part of the metric. That will appear on the right-hand side here, and we obtain this solution. We obtain a solution with these constants. All right, so then what we have got is we've got some source. This example here is when we have the source is two bodies in circular orbit around each other. We've got a solution in the interior, we've got a solution within the shell, and we've got a solution within the exterior. Okay, so we've got these three solutions. All right, and we've got a whole lot of constants have been introduced. And in order to explicitly solve the problem, we've got to get rid of a lot of these constants. So we've then got to ask ourselves, what conditions can we impose that will get rid of some of them, that we can use to eliminate some of these constants? All right, so one condition is that in the exterior, there will be no incoming radiation. So that puts that C in E equal to 0. Or rather, it constrains it. Then what we would have is that we've got a uniform coordinate system. So as one goes from one domain to another, the metric must be continuous. So we've got 4 metric functions, so that imposes 4 conditions of continuity at the boundary between the interior and the shell, and another 4 conditions of continuity at the boundary between the exterior and the shell. And finally, what we're going to have is that we must allow for the possibility that the effect of the shell will be to introduce a small incoming gravitational wave. All right, but that wave would then just pass through the center and come out again, and there'll be a relationship between the additional outgoing wave and whatever incoming wave is generated by the shell. And that in mathematical terms, so this slide just states in mathematical terms what I've said on the previous slide. So we fix CNE to be something. The continuity of the metric gives us 8 conditions at R0 and at R0 plus delta. Right, I would also comment that the Einstein hypersurface equations contain second derivatives of J and U. So we expect that the first derivatives of J and U must be continuous at R0 and R0 plus delta. So we've checked that provided there's continuity of the metric, these conditions are satisfied. This is a strong consistency check of the calculations. I mean, one can just introduce some deliberate mistake in this calculation, change a plus to a minus in one of the equations, and it doesn't work. And then finally, there's a relation in the interior region between the incoming and additional outgoing gravitational waves given by this relation. The outcome is that 2 degrees of freedom remain, B0I, C3I, which are gauge freedoms, and the expression for the gravitational wave strain only involves C40. I mean, as happened earlier on in where is it here? All right, this solution also had 3 constants, C30, B0, and C40. All right, but the actual expression for the outgoing wave only involves C40. So we'd get the same thing here, and the final answer we get for the way in which the shell modifies the gravitational wave is given by this formula here. So each of the terms containing ms represents a correction to the wave strain in the absence of the shell. Right, so when ms is 0, we're just saying that h is equal to h0, is equal to that formula that I wrote down a few slides ago. And then the correction terms are given by the proportional to the mass of the shell. So the first correction term, ms, 2ms over r0, represents the well-known gravitational redshift effect. So one can apply the time dilation formula, and one can show that doing that then gives rise to this term. So it's encouraging that going through all this calculation, which had nothing to do with the time dilation effect, the first correction we get is just the gravitational redshift effect. The second correction term is out of phase with the leading terms, and so it represents a phase shift without changing the energy. That's because the magnitude of the wave is the square root of the sum of the square of the real part plus the imaginary part, right? And all right, because we're working to linear order, the imaginary, when you square this, you get ms squared, which is n ignorable. And the third correction term represents a partial reflection of the gravitational wave by the shell, and leads to the possibility of a matter shell causing a gravitational wave echo. All right, now echoes are interesting. There's been previous work on whether the astrophysical environment might modify a signal leading to the possibility of an echo. I mean, first of all, it's been suggested that there are various exotic theories of gravity in which when two black holes merge, or rather in which the solution to a black hole does not involve an event horizon. And in some cases, this would lead to an echo. So on the theoretical side, there have been proposals that echoes can be produced if the theory of gravity is modified. There's also been an argument, well, in 2017, that echo was actually observed in the LIGO data of the first gravitational wave event. All right, and although that idea is, I mean, the consensus now is that there's no echo in that data. Although when we did this work, started this work a few years ago, that idea was very much around. So it was important then to look at the possibility of a gravitational wave echo being produced by non-exotic physics. So could a matter shell have produced the suggested echo? So that's a question we would have asked a few years ago. Now one would say that there really was not an echo in the GW, in this GW data, so the question's not relevant. Okay, but if it was relevant, the suggested echo was 0.3 seconds after merger, so allowing for the light travel time, the shell would have to have a radius of 45,000 kilometers. Magnitude of the echo was 0.099 times the original signal. Using 132 Hertz for the frequency gives a shell mass of 740,000 solar masses. Now, such a mass within a radius of 45,000 kilometers would constitute a black hole. So the scenario of an echo caused by a shell can be discounted for that event. However, what's interesting is a much smaller shell radius would avoid an unreasonably large shell mass, but the effect would be seen as modifying the original signal rather than an echo. So it would be as though one's one's talking in a room with solid walls, and the signal gets slightly the sound gets slightly distorted by echoes of the walls. You can't talk about it as an echo because it gets mixed up with the signal rather than coming later. So the magnitude of the echo term can be written like this: 2ms over r0. Now, this always has to be less than 1 or you have a black hole. R0 is the radius of the shell, ms is the mass, and so that has to be less than 1. And then times the wavelength of the gravitational wave over 8 pi r0. So if the wavelength is comparable or longer than the shell radius, you could get a significant effect. All right, so we now want to look at applying this theory to real signals. Real signals are burst-like rather than monotonic. So in order to use the formalism, we first transform a signal into its frequency components, apply the modification formula to each frequency component, then do an inverse Fourier transform. All right, and we note that the model assumes small deviations from Minkowski, and the background is static and spherically symmetric. So, I mean, it's not exactly applicable to astrophysical situations. So it's more what we're going to get up with is more a guide as to what would happen than a precise prediction. All right, so this, but to show the type of effect that one could have, this is the effect of no, suppose there was a matter shell of radius 900 kilometers and 60 solar masses around the event GW150914. This is how the signal would be modified, and I mean it's measurable, so it's not a tiny effect. I mean it's not huge, but it's measurable. So the original signal is in blue and the modifications in red. I mean, what you see is that at lower frequency, which is longer wavelength, the effect is bigger. And at the higher frequency, as the black holes actually coalesce, the frequency is much higher and the effect is smaller. This is the quasinormal mode of a black hole following a binary neutron star merger. Quasinormal mode in blue, quasinormal mode plus shell effects in red. I mean, again, I mean, this effect is really quite small. And I mean, what we're thinking of this, of there was, what, in 2017, there was a merger, the first merger of two neutron stars was detected, and we're applying it to that type of data. In that event, there was no post-merger signal. The signal died at merger. So no quasi-normal mode signal was detected. So one can't ask the question whether this was observed in data or not. And then finally, we're looking at how one might modify a core collapse supernova, the initial burst in blue, the initial burst plus shell effects in red. I mean, again, you see that there are small but noticeable effects. All right, now I want to go on to viscous damping of gravitational waves. All right. So, I mean, although I haven't shown it, during the first part of the talk where we talked about the phase modification, during that part of the talk, we were considering the shell as being composed of dust. We're now considering that it's composed of a viscous fluid. And now, assuming geodesic motion, the velocity field, which was worked out in the previous papers, is given by this formula here. Okay, so it's fairly straightforward. Right, then the viscous effect is given by the effect of viscosity on the matter is driven by the shear of the fluid, And to work that out, one needs the shear tensor. And the formulas are standard formulas all given here. So the expansion is the divergence of the velocity field. PAB is it projects onto a direction orthogonal to the velocity direction, and sigma AB is the shear tensor, which is given by this formula here. Okay, I mean, essentially the shear tensor is some form of gradient of the velocity field. They're making the usual of separation of variables, ansatz. We end up with some remarkably simple expressions for the shear tensor components. I mean, first of all, it turns out to be a gauge-independent quantity. The gauge constants B0, C30 disappear. All right, and these quantities are really quite simple. I mean, again, they're functions of R times sinusoidal dependence in time times a spherical harmonic. We also find that the fluid expansion is 0, so the bulk viscosity is irrelevant, and only the shear viscosity has an effect. And actually, we certainly expect the expansion to be 0. Well, we know that gravitational waves do not change, do not cause a fluid to change its volume. So the rate of energy loss per unit volume is given by this formula here. This quantity is then integrated over a shell of radius r and thickness delta. The integration over the shell is easy because we've decomposed our solution. I mean, part of our separation of variables, ansatz, was to decompose it into spherical harmonic basis functions, and they are orthonormal. So that means that they're orthonormal with respect to integration over the sphere. So integrating one spherical harmonic times another is absolutely trivial. You either get 1 or 0. The average rate of energy loss to the shell is then given by this formula here, where F denotes the average of some quantity over a time period, and we've used the standard averages for cos squared, sine squared, and cos nu, sine nu. Now, if we compare the rate of energy output of gravitational waves is given by this formula here, so combining this one and this one, we can write down the energy transmitted to the fluid by gravitational waves in terms of the energy within the gravitational waves by this formula here. So energy conservation means that the energy absorbed by the viscous fluid is balanced by a reduction in the gravitational wave energy. So we can then write down, so the previous result then takes this form here. And if h represents the magnitude of the gravitational waves, h squared is proportional to the rate of energy flow. So when you take the square root of and this quantity is small, of 1 minus 16, you get 1 minus 8. Right, and this is then just a differential equation. You can rewrite this as dh dr equals something which involves r, and then you can integrate it. So we end up with this formula here, which again is, and the integration is really easy because you're either integrating, you get dh over h, which is in log, and then when you exponentiate it to get rid of the log, that's where the x comes from. And 1 becomes r, this, and then this is just standard integration of a polynomial. So in order to understand what this formula is saying, there are 2 useful special cases. Ri, Ro be the inner and outer radii of the shell. If Ri are much larger than the wavelength of the gravitational waves, then what we have is that h at the outer radius is equal to h at the inner radius times the exponent of minus 8 pi eta times this thickness of the shell. And that's exactly what was obtained really by Stephen Hawking almost 60 years ago. So that result's not new, but it's certainly, I mean, important that the work recovers a known result. All right, if Ri is much smaller than the wavelength, and we write here, now we're going to write R, the outer radius is some constant times the inner radius with alpha bigger than 1, then we get this formula here. And as Ro goes to infinity, or alpha becomes large, this reduces to this formula here. All right, but the damping effect is reduced by only a little for a shell of finite thickness, because 1 minus alpha to the minus 7, goes to 1 very fast. It's 0.99 for alpha equals 2, and 0.5 for alpha equals 1.1. So if one's looking at order of magnitude effects, this is a useful formula to work with. And then the interesting thing about this is, although eta times r may not be, it's difficult to see how that can give you, when you translate into SI units, how that can give you a number that's comparable to 10 to the 36 to give you some noticeable effect.
Hi, it looks like.
Sorry, I don't know what happened then. Suddenly something just dumped. Okay, let me start screen sharing again. Okay, is that back? Can people see again?
Perfect.
Perfect. Okay. Who knows what happened then? Okay. So where were we? All right. The damp. All right. Now. Okay. So in order to interpret this, we'll now look at whether this is astrophysically significant. All right. So first of all, some caveats. One important comment is one would expect a numerical relativity simulation that allows for matter viscosity, and with gravitational wave extraction far from the source, would include all the above effects. However, gravitational wave extraction is normally calculated using a modified quadrupole formula, and current models do not include shear viscosity. So we found that viscous damping can be significant for primordial gravitational waves and for core collapse supernova. For core collapse supernova, includes processes with gravitational wave emission in the range 100 to 1,000 hertz. So the wavelength is between 300 and 3,000 kilometers. The size of the source region generating the gravitational waves is somewhere between 10 and 28 kilometers, according to different estimates. So then the lambda over r can be, then the matter shell is outside that. Lambda over r can be large. It can be up to 100. Take that to the power 8 and you've got a big number. Reported values are up to 10 to the 25 for the viscosity. So we now plot a surface on which the damping factor is a half. So values of eta a little above the surface would lead to almost complete damping. Those a little below would lead to almost no damping. So what we see is that this 10 to the 25 is given here. So if you're right in the upper corner, you're talking about high frequency signals from a core collapse supernova, and that the core is really at the upper limit, then there would not be much of an effect. All right, but there are big regions in this diagram where you could have something like, if the viscosity is 10 to the 20, you would expect more or less complete damping whatever over all whatever the radius of the core. So what this is showing is that in core collapse supernova, the effect of gravitational wave interaction with the matter is highly important as far as the gravitational wave signal is concerned. We're not talking about a 1 or 2% effect as we showed with the phase effects. This is of the order, this can be of the order of 100%. It's highly significant. Primordial gravitational waves are another possible area where gravitational wave interaction with matter could be important. Primordial gravitational waves, the idea is that they're generated during inflation, but I mean, it's highly uncertain as to the precise form of the waves. There are many different ideas about it. But in order to get an idea, we'll take some typical values. So the end of inflation would be about the universe was 10 to the minus 32 seconds old. Temperature 10 to the 27 to 20 to the 8 degrees Kelvin, and the scale factor 10 to the minus 27, where it would be 1 at present. Hubble rate doesn't change during inflation and is taken as A over A dot, which would be 10 to the minus 35. Which gives the horizon scale as 3 times 10 to the minus 27 meters. Current and planned gravitational wave detectors, I mean, that's everything from pulsar timing up to LIGO, operate in the frequency range 10 to the minus 9 to 10 to the 3 hertz, which gives you a wavelength of 10 to the 5 to 10 to the 17 meters. And at the end of inflation, when you multiply by this 10 to the minus 27, you get that you'll be interested in gravitational waves in this wavelength range, 10 to the minus 22 to 10 to the minus 10 meters. During inflation, this Weinberg estimated the viscosity can be as high as 10 to the 58. And this means that you're going to get, again, we would get huge effects. In fact, you would get an effect even when at a viscosity as low as 10 to the 25. So what this is showing is that, I mean, again, the viscous absorption by matter of gravitational waves in this scenario for primordial gravitational waves can also be highly significant. All right, so to conclude, changes to both phase and magnitude occur when gravitational waves pass through a shell of matter, and these changes are large enough to be measurable. The effect of viscosity and gravitational wave propagation was calculated, and the known result for a viscous shell was recovered when the wavelength is much smaller than the radius of the shell. But when the wavelength is much bigger, it was found that viscous damping can be a highly significant effect. A number of core collapse supernova models have been proposed. It was found that in many cases, significant viscous damping of gravitational waves was predicted. It was also found that there are feasible values of early universe parameters that imply almost complete damping of primordial gravitational waves. Gravitational waves are detected from a core collapse supernova, but not over the whole frequency range, and this would constrain a combination of core radius and viscosity. And if primordial gravitational waves are detected, then the models discussed here would be excluded. Okay, thank you.